there's some announcements. So this will be the last regular lecture. Today we're going to talk about islands. I'm doing my final project on replica wormholes. A presentation tomorrow. So today we're going to do islands, and then I'll spend the beginning of the presentation session tomorrow talking about replica wormholes. That part will be on video, so people who can't make the first presentation session can watch it there. Yeah.
If it's in PSP 401, are we going to use the blackboard, or is?
We're going to bring the blackboard in.
Okay.
Yeah.
Okay.
Yeah.
I don't know if I had to make slides or something.
Okay. So. Today we're going to talk about the island formula. We've talked about generalized entropy, how you can use it to calculate the entropy of a black hole. We've talked about holographic entanglement entropy, which relates, calculates the entropy of a boundary region in anti-de Sitter space. The island formula is an extension of this. As you'll see, it's pretty similar, but the setup is a bit different. Okay, so the formula is the same, but the setup is different. So the setup is the following. I'm going to artificially divide space into a region where gravity is important, where you have black holes and stuff, and a region where gravity is not that important. Okay, so over here, gravity is important. And by gravity, I really mean nonlinear gravity. Linear gravity is no big deal. That's just quantum fields. And over here, nonlinear gravity is not important. And the idea is that we want to calculate, we have some region R. Okay, so T is going this way. We have some region R at some time, and the island formula is let's see, how am I going to fit everything? Well, I'll start over here. Okay, so let me write the formula. It's a formula for the von Neumann entropy of the quantum fields in region R. Yeah.
So in this other region, you can still have linearized perturbations around a certain time.
That's right.
So you can have gravitational waves.
Yes.
Okay.
Yeah. So S of rho sub R, and I'm going to write the formula. This formula is part conjecture, it's part derived. I'll try to sort of explain what the situation is. It's the min over I, the x over I of a quarter the area of di plus S of rho tilde I union R. Okay, I'm going to explain all the pieces that are showing up here. First of all, I. So I is a region over here in the gravity side, where gravity is important. And so I is chosen dynamically as the extremum of this generalized entropy functional. So let's see, so that's I. I need to explain the deal with the tildes and everything. So rho, when I write a density matrix with no tilde, I mean the purported or conjectural exact density matrix in quantum gravity. And when I write rho tilde, I mean the state as calculated by the ordinary methods of Q of t in curved space. So what's the difference? Well, we already expect from the black hole information paradox that ordinary Q of t in curved space is not quite right, because it gives the information paradox. But you can use it to calculate something, and I'm calling that something rho tilde. The idea is that this is sort of a coarse-grained thing that's discarding some non-perturbative effects of quantum gravity. And so if we look at this formula here, it's pretty similar to the holographic entanglement formula. In holographic entanglement, we had a lower dimensional region sitting here at the boundary, but otherwise the formula is pretty similar. The other big difference is that region I is just free floating by itself. That's why it's called the island formula, because it's like an island that's sitting there by itself. Okay, it's just free floating, unlike in holographic entanglement entropy, where it was sort of sticking out of the boundary region. Here's just this free floating island. Yeah.
Let's see. So the EXT sub I thing means that something is a saddle point. It means that
Yes.
It means that can you say again what that means?
That means we extremize the thing in brackets with respect to the choice of region I, or you can think of it as being, all this stuff really only depends on the boundary of region I. So, for example, if I like wiggle region I, if I make region I like a little bit bigger, the generalized entropy in brackets should be stationary under those deformations. It's a minimum in the space direction and a maximum in the time direction.
Sorry. One thing that's a little confusing is rho tilde is calculated using ordinary methods in curved space, but it includes contribution to the region I where gravity is sort of like non-linear.
Yeah, I don't mean I don't mean a fixed curve space. I mean a full-blown calculation, like Hawking's calculation, for example, is a full-blown calculation of Q of t at curve space where it's back reacting, and you could have a black hole. There could be a black hole over here that's evaporating. That whole calculation gives some density matrix, and that's the one that shows up here.
So in terms of the calculation, what would be different from rho then?
Well, see, the calculation that Hawking did, we think has something wrong with it. And this is so we don't think calculations like that can give you the exact density matrix. We think they give you something else. And this is a proposal or conjecture for what we believe to be the von Neumann entropy of the exact density matrix, including all quantum gravity effects, including the ones that Hawking missed.
So computationally, rho and rho tilde will be calculated differently, and we kind of know how that happens.
Well, computationally, this is funny. We certainly know how to calculate rho tilde. That's just a standard kind of calculation. We do not know how to calculate rho. To calculate rho, you would need to know string theory or whatever the correct UV completion is, and you'd have to use the complete microscopic details of that theory to calculate rho. But what's very surprising is that according to this formula, even though we don't know how to calculate rho, we know how to calculate its entropy without using any string theory or anything. Yeah.
Wouldn't this thing just be extremized by letting I go to 0?
That is always one choice, but fun. Sometimes it's not the only choice, and that's when fun ensues.
But won't you just you let the smallest area if you let I go to 0?
Well, we'll see examples where it's let me tell you now when it happens. It happens when there's a lot of entanglement between region R and region I. See, because when there's a lot of entanglement between region I and region R, that would contribute, well, then we're comparing S of rho tilde with an I and S of rho tilde without an I.
Yeah.
Okay, so when you're talking about von Neumann entropy, including region I can make that von Neumann entropy go down if the stuff in there is entangled with the stuff in there. So the island formula is going to be non-trivial and important and interesting when there's a huge amount of entanglement between R and I. And I say a huge amount because this first term, the area term here, this is 1 over G Newton. This is a classical term. The second term is the von Neumann entropy, so we need the von Neumann entropy to be able to be big enough to compete with the classical area term to get something interesting.
And is it expected that this is like exactly the entropy, like the von Neumann entropy that you would get if you use string theory, or is it just?
It's approximate. Well, it's approximate. I mean, we can add corrections, like curvature corrections, and get a better and better approximation. Whether that's exact in some sense, if you include all those approximations, I don't think we know. I'm not sure we even have a well-defined way of doing that. This is the leading term. There's a second piece of this conjecture, which is, I guess, logically distinct conjecture, but it's sort of a corollary of this, and this goes back to holographic entanglement entropy and the story of error-correcting codes and tensor networks and all that. Remember what we said about holographic entanglement entropy, that let me draw the holographic picture again. There we had a boundary with a region A, and there was this region A tilde coming out, and it was this region A tilde that was being extremized and showing up in this formula. And in this case, we said that not only does this extremal surface calculate for you the entropy, it tells you the region that's dual to region A. In other words, all the physics in A tilde can be reconstructed in principle if you know the density matrix of region A. The same conjecture applies here. Okay, so the conjecture is that all physics in I, this is in I after doing the extremization, the true island, can be reconstructed from rho sub R, in principle, similar to ADS-CFT. So this is great because one of the big problems of ADS-CFT is that it only works in ADS. We think it's a good way of thinking about quantum gravity, not just in ADS, but a good model for quantum gravity in the real world and in local regions, and a good way to think about emergent spacetime. But we were always kind of stuck in ADS for actually ever calculating anything, and you could wonder if it had anything to do with regular gravity. Well, this is a situation where you seem to be able to do something similar with no ADS, no cosmological constant anywhere in the game. Now, you have to get an island to appear. So this is going to be non-trivial, and what we're basically only going to find islands in black hole interiors. It's going to be an island in the black hole interior. But it gives us something like holographic duality, something like ADS-CFT that applies to black hole interiors. Yeah, I'm going to do that for my final project. let me tell you the short version now. I've already talked about the derivation of the holographic entanglement formula. The derivation of this formula is basically the same with one new wrinkle, which is that when you draw the when you do replica calculations in gravity, the one new wrinkle is that because you're doing a calculation in gravity, you can have topology, you can have interesting topologies. And, sorry, that's a terrible picture. That's not what they look like at all. Let me draw them this way. When you have your replicas in gravity, since it's gravity, you can have interesting topologies like this one that contribute in the replica method. And it's the contribution of those topologies that lead to this formula. Other than that, other than saying, oh, you better include these topologies, once you do that, the derivation is exactly the same as the derivation of the holographic entanglement formula that we discussed last time. But I'll talk about that tomorrow / on the video. Okay, are there any other questions about that? This is all going to be conceptual today. We're not really going to calculate these things, but I'm going to explain how they show up in black holes and answer questions, basically. Okay, so good? So why do they matter? Well, for this, we're going to revisit the page curve. And I've sort of hinted at this before, but now let's go through it in some detail. So let's see. So I'm going to, the page curve here. Okay, so remember what the page curve looks like. We have a black hole that's evaporating, and we're measuring the von Neumann entropy, calculating the von Neumann entropy of the radiation. So Hawking says it does this. I'll call this S of rho r S of rho r tilde. So this is what Hawking predicts. Rho r tilde is just the density matrix as calculated by the methods of QFT in curved space. That's the calculation Hawking did, and the answer was thermal. So this is what the entropy looks like. This is when the black hole's gone. So the other thing we plot is the quarter of the area of the black hole. That black hole is shrinking down to 0 size. And recall that the information paradox kicks in when these two lines cross. Okay, because the only place you can have, the only way you can, you're in a pure state, we're assuming this is a pure state. The only way that the entropy can, the only way that radiation can have entropy is by entangling it with the black hole. But if the black hole only has this many degrees of freedom, you can only get so much entropy. This is the maximum amount of entropy you can make by entangling with it. Okay, so the paradox kicks in here, which is called the page time. T page. Okay, so that we discussed before. Now let me draw the picture in Lorentzian signature. This calls for some colors. Okay. The experiment we're doing is that, first of all, we made a black hole. So the black hole, let's say, is a collapsing star. So here's the surface of the star. There's a spherical star that collapses, makes a black hole. And we are going to sit, it makes a black hole of some Schwarzschild radius. We are going to sit comfortably, let's say, like 1 million Schwarzschild radii away. Out here. So say this is at 10 to the 6th of the Schwarzschild radius, and here I mean the Schwarzschild radius of the black hole that was initially formed. It's evaporating, it's shrinking, but and we're gonna sit out here and we're gonna collect the Hawking radiation that gets to us. So we're gonna consider a region R, which is a function of t, because we can move the endpoint of this region R, and we're interested in calculating the von Neumann entropy of rho sub R. And that's the von Neumann entropy that I've plotted for Hawking's calculation on the left. Okay, so what happens when you use, so now we're gonna do this using the island rule, the island formula that I just wrote. So what happens, so first of all, I equals nothing is always extremal. Okay, the nothing island, the empty trivial island, is always an extremum of the generalized entropy. So let's call that S1 of rho sub R, meaning the contribution to the island rule from the trivial island. Okay, so the island rule tells us that the von Neumann entropy is 1/4 of the area. That term is just 0. It's a trivial island. And then there's the S of rho tilde term, which in this case is just S of rho R tilde, which is Hawking's result. Okay? So far so good. if there's no island, it's just giving back Hawking's calculation. So what happens, however, is that for t greater than some critical time tc, a new quantum extremal surface appears. So quantum extremal surface, meaning refers to the boundary of the island, the di. So for t greater than tc, a new quantum extremal surface appears. It's near the horizon, actually just slightly inside the black hole. So on the picture, for a given choice of R, if you're at t greater than tc, there's an island whose endpoint is, say, right here. So this region here is region I. That's a spherical region. Got to rotate this plot around in your head. That's basically the entire black hole interior. It's slightly inside. That will not be important at all. What's more important is where it is along the horizon. And that depends on where we are in t. Okay, so as we go forward and as we wait longer and collect more Hawking radiation, this island will slide up the horizon of the black hole. I'm going to come back I'm going to come back at the end today and discuss why it appears in a very interesting place along the horizon, having to do with the scrambling time. I'm going to come back. And for now, it's just somewhere along the horizon. Yeah.
No, I and R have to be separated, right?
Correct.
So, I mean, couldn't we like pick any time slice that we want, and then there would have to be like an eye on that time slice?
No, I is a region, it's extremized over space-time.
It's extremized over space-time. But like this picture that you drew over there, it looks like it's at like one time.
Yeah, I didn't have to draw it that way. They have to be space-like separated, but since we're extremizing,
Yeah.
we're really extremizing in space-time. We're picking a region I somewhere in space-time.
So if this extremization is done, if this is a non-local in time procedure, how do you track something over time? Like if there's no sense in which it's
Well, Eddie, so think of, let's give this, let's put a label here, which is T sub R. Okay, T sub R is the time of this point here. Okay, then the endpoint, let's put a coordinate lambda along the horizon, and lambda will be a function. Lambda of the island will be a function of T sub R. So like, if I put region R here, I will go there. If I look later, like here, I've collected more Hawking radiation. Then your region I is going to go up to here. Okay, so as region R moves forward in time, region I also moves forward inside the black hole.
But I thought that for the first thing you needed to have information about the whole space-time before you did the extremization, right?
Well, yeah, we extremize over all of space-time, but why is that a problem?
I mean, I just don't know when, like, if you average something or extremize something over all time, how do you get a local quantity in time at the end? Is what I'm confused.
Well, I'm not sure what you mean by local in time. I mean, we choose a region R in the island formula. We choose a region R, and for that region R, we do this extremization procedure. It depends on R because of this term, and so for any region R, there's an associated region I. So let's look at the entropy.
I itself has to be like space-like though too.
Yes.
It doesn't have any like loops or anything.
That's correct. I is a spatial region. I mean, everything in this formula depends only on the boundary of region I. So you could really think of it as the diamond. You could think of the island as the whole diamond associated to what I'm calling the island. Either way, it doesn't matter. It really only cares about the boundary.
Tom?
Yeah.
So in this case, the QS is allowed to lie inside the horizon without violating the homology condition because it's an evaporating black hole, right?
No, that's not why. It's because every region is it's because these region I is homologous to nothing. Oh, sorry. You're saying that's related to it being evaporating?
Yeah, for eternal black hole,
I don't think the homology. It's true that for an eternal black hole, it comes outside the horizon.
Yeah.
But I don't think that has anything to do with the homology condition. Whether it's inside or outside, I mean, we could deform it to be outside. So those don't have any topological difference. That has to do with something else. Other questions?
Does it matter how far back the island extends behind the horizon?
It goes all the way. Yeah, it does matter because the boundary of the island is what's important, and there's only this outer boundary. It doesn't have like an inner boundary in here. It goes all the way to the this is the origin in polar coordinates. So it's like a blob inside the black hole. So if we let's calculate the entropy associated to this island.
But it doesn't actually have to be spherically symmetric. It's just the extremization is spherically symmetric.
Well, if it's, yes, it doesn't, no one's requiring it to be spherically symmetric. I've drawn it as spherically symmetric just because I have to, because I'm human. But if everything else is spherically symmetric, then it will be. But no, we're not putting that in by hand. So let's calculate the von Neumann entropy from the island rule for this island. Not that we already calculated the contribution of the trivial island. Now we have this new quantum extremal surface, and we want to calculate the von Neumann entropy in the island rule. Well, it says it should be a quarter of the area. Well, that's just a quarter of the area of the black hole. Okay, so it's because the edge of the island is basically sitting on the horizon. So we get a quarter of the area of the black hole. Now, it's an evaporating black hole. Okay, so I have to say the black hole when. We're going to come back to that. For now, let me just say at some time that's determined by TR, which is going to be roughly, it's roughly the black hole at the time you'd expect. Like, this is happening very slowly over a bazillion years. And so you can ask, like, what size is the black hole right now? Well, that's the size that goes in here. There's going to be a very interesting subleading correction to that statement, which is the scrambling time. So I'll just call it, for now, black hole at time t. And then there's the von Neumann entropy term. Okay, S of rho tilde I union R.
But what did you mean by the black hole now?
I mean, the black hole's evaporating, so I can't just ask what the area is.
Yeah.
But since it's evaporating very slowly, it's really just a quasi-static process where it's always basically a Schwarzschild black hole, just with a very slowly changing Schwarzschild radius.
Yeah.
So I'm referring to the instantaneous value of that Schwarzschild radius at time t.
In what coordinates?
Schwarzschild coordinates. There's a coordinate system in which, at a given time, t, to a very good approximation, there's a slice here which is the Schwarzschild metric.
Or I guess it could be like Kerr or something.
Right. Yeah. Okay. So what is this second term? Well. Let's think about Hawking radiation. So what is Hawking radiation? Hawking radiation is pair creation at near the horizon. And when you create Hawking pairs, you create entangled pairs that do something like this. Okay, so one of them ends up in region R, and the other one is trapped inside the black hole. So that's why Hawking radiation appears to have lots of entropy, because that Hawking radiation appears to be entangled with these interior partners. But if we wait a long time, there are lots of these Hawking particles corresponding to lots of entangled partners in the interior. But these do not contribute to S of rho tilde I union R. They simply do not contribute. This is 0. Because the whole point is that they're entangled, so together they make a pure state, so they have no von Neumann entropy as long as you can see both of them. If you could only see one of them, then you're back in Hawking's situation and you get a large entropy. But when you can see both of them, that term drops out. So the contribution of the non-trivial island is the area of the black hole. And therefore, the island formula in this context says that S of rho sub R is the minimum of these two solutions, that is S Hawking and a quarter of the area. That's that last min happening in the island formula where if you have multiple extrema, you should pick the one with minimal entropy. Therefore, on the page curve, you have Hawking's curve coming from the trivial one. The non-trivial one starts like here somewhere. It doesn't exist right away, but there's a critical time where that island appears, but is subdominant. But when you get to the page time, the non-trivial island takes over. So according to the island formula, the true von Neumann entropy follows Hawking's calculation until the island becomes the minimal entropy contribution. At that point, it turns over and follows the area curve back down to 0. So first of all, so what do we learn from this? Well, first of all, it's consistent with unitarity because the von Neumann entropy of that pure state goes back down to 0 8 times as it must in a pure state. But not only is it consistent with unitarity, it's also exactly the curve that was predicted by Page for sufficiently random, complicated quantum systems. So remember when we first talked about the Page curve, we said that if black hole evolution is sufficiently complicated, then it should have this sort of phase transition property where it follows Hawking's curve until it suddenly turns over and follows the area curve. We talked about that in terms of this like random qubit model. And that's exactly what's coming out of the island formula. Geometrically, this is the no island, and this is the island part of the curve. Yeah.
So in this example, you have to look at two different times, right? There's a time before TC and then one after that, and you extremize over that, right? And then over that time, the region R itself changes.
Yeah.
So what is it the entanglement entropy of now? Like, is it
It's the new region R. I mean, region R is itself a function of T.
right?
Okay, so for any given region R, there's a
So I mean, in this calculation, there's two different regions R, right? One before
Yeah.
TC, the other one.
yeah. Region R is a function of T,
Right.
and region I is also a function of T.
And then this value that you calculated.
Let me say it's a function of T sub R. They're both functions of T sub R, which is the value of Schwarzschild T at the endpoint of region R.
And so the value for S rho R would be different at these two different times, right?
Yes?
And in this final answer that we calculated, what is this the entropy, and what time does this correspond to?
Sorry, here?
Yeah.
Oh, at time T. They're both functions of TR. And that's what we're plotting. We're plotting it as a function of TR.
Nice.
Yeah.
Can you say anything about the turnaround point?
Well, such as?
The point at the top. When it turns over.
Yeah.
Is it smoothed out by something, or is?
Yeah. Yeah. In this approximation, there's a discontinuity in the derivative that is smoothed out by subleading corrections in the 1/n expansion that we haven't included here, but you wouldn't see them on this plot, but it's a little bit smooth. That go beyond the replica wormhole approximation. Yeah.
Do you think the island formula is true for any semi-classical quantum states?
I think so, but I wouldn't say it's been proved or anything. Yeah. Why? Do you have a counterexample in mind?
No, I just think like if you, the only way we know to show a replica wormhole is somehow assume the spacetime is smooth. If I have something like the entanglement is discontinuous, there's some discontinuity when the gravitational region and the non-gravitational region.
Yeah, I agree that, the replica trick, the gravitational replica trick, needs Euclidean path integrals to derive it, and you can't make any state with Euclidean path integrals. You can only make sort of nice smooth ones, but you can make a very good approximation to any state with a Euclidean path integral, so that makes me think that it's true in general, but I wouldn't say it's been derived. There could be interesting loopholes in that argument. Other questions?
All this is true for typical states, right? So you can always generate some states which are atypical, and then this won't work.
That is a very interesting question. Okay, so I'm not sure what you mean by typical state. I would say this is true for...
I mean, we are assuming that the black hole evaporation process is sufficiently random that you can average over unit race. And
No, I don't think we're assuming that at all. I think that we're... no, I mean, I haven't assumed anything about the quantum state of the black hole. You know, Page did when he said that this should be the answer. But in this calculation, we just did gravity. We didn't assume anything about random quantum states or anything. I would say we did this calculation for black holes that formed by collapse. And black holes that formed by collapse from a relatively simple initial state. Okay, like in this case, the relatively simple initial state was the star. You can make a star by inserting some sources in your path integral. The black hole has e to the s states. Okay, so the subset of those states that you can make by a relatively simple collapse is tiny. You can only make a tiny fraction of black hole states by collapsing relatively simple initial states. Okay, so in fact, the assumption that we formed this black hole with some reasonable, like, semi-classical evolution is a very atypical assumption. I would say we're studying very special states in order to be able to do this calculation. And if you ask about typical states of a black hole, like, list the e to the s states and just pick one at random somehow, we don't even know if it has an interior. We don't know if it has a semi-classical description. We know very little about how to describe typical states in quantum gravity in black holes. So I think that's really an open question.
So then literally the qubit model and this calculation lie in two different regimes.
Well, not exactly. I would say the qubit model includes this regime. The qubit model actually does not require a random state among the e to the s. It only requires it to be a little bit random. It only requires it to be scrambled. I guess, I don't know if I want to get into it, but you can scramble very quickly. Okay, scrambling is a much weaker statement than typicality. Scrambling just means that information is spread over all of the e to the s degrees of freedom. Or sorry, all over the whole s degrees of freedom. Whereas typicality is much harder to achieve. It's something that takes a very long time. Like, you can scramble in time log s, but it takes a time e to the s to reach a typical state. And I think the Page argument only requires scrambling. So the Page argument applies both to the actual situation of a black hole, which is a relatively short amount of time evolution required, and it applies to typical states. But this picture, we don't know if it applies to typical states because we haven't weighted a time e to the s. Yeah.
So I think you said that the smoothing of that the cusp or or the, that thing, happened because, you said because of subdominant saddle points?
Well, subdominant topologies, they're not actually saddle points, I don't think.
What does that mean, topologies?
Well, you have to ask me that when I talk about replica wormholes, because this is derived by replica calculation, and the point is that it comes from topologies where the replicas are connected, like they grow wormholes between them, and the smoothing of this tip comes from topologies that are more complicated than the ones that I'll draw tomorrow. Yeah.
Is there a way to think about it without making reference to the replica method? That's kind of like what I was asking earlier, I think.
The tip?
Yeah. The replica method's like a trick.
Yeah, no, there is. So in fact, I think you can use Page's method. Well, I don't know if you'd call that a black hole calculation, but Page's derivation of the Page curve is only sharp at leading order, and you can repeat Page's derivation and ask, what does Page say about the smoothing of the tip? And that agrees with this calculation that you get by including more topologies in the path integral. I don't know any other way of thinking about it.
So I thought these were also like saddles, right? But they're just not replica symmetric.
Are they? Okay,
So
I don't remember.
why do you say they're not saddles?
I just don't remember if they're saddles or not. Maybe they are. So let's talk about the interpretation. Well, as I keep emphasizing, all of this holographic entanglement, island formula kind of stuff is really two things. First, it's a formula for calculating entropies, but second, it's a way of understanding how holographic dualities work and who's encoded in who. Okay? So the interpretation in this case is that the physics in the island that is in the black hole interior can be reconstructed from the Hawking radiation, in principle, after the Page time. So you're patiently collecting the Hawking radiation. You wait and you wait and you wait, and you're starting to get discouraged because you haven't learned anything about the black hole interior. And then you collect that one extra bit right at the Page time, and you suddenly have access to the physics inside the initial island. There's some initial island that will form right when you cross the Page time. Yeah.
What do you see before that time?
What do you mean? What do you see?
If you look at your collected data, is it like some
you just see a thermal
fuzzy image, basically, or
no? What? No, you see Rho sub r is just exactly thermal.
But that like one extra bit, and then everything becomes clear, or like?
Oh,
I guess that's what I'm asking. Like,
I mean,
is there like some way to understand like how resolved the island is in the radiation, like before? Is there a notion like that, or?
Yeah, I don't think you suddenly get a whole lot of information. I think what happens. So we have to be a little careful when we talk about being able to reconstruct the physics in region I, because if you act with an operator in region I, it'll back react, and it might change region I. It might even eliminate region I entirely. So when we talk about reconstructing the physics in region I, it's an ability to approximately reconstruct certain kinds of small fluctuations. And I believe, although this is an interesting question, I'd really have to think about it more, but I believe what should happen is that when the island first appears, you only have the ability to, you do have the whole island, but you have a very limited set of operations that you can do on it without messing up your reconstruction ability. But if you had, but you can do simple operations. So like if you had dropped in 1 qubit 100 years ago, you would be able to now read that qubit in principle.
Can you maybe say a word or two about what you mean by simple?
I don't really want to get into that.
Okay.
Partly because I don't have like a simple explanation of what I mean by simple. I would say that the answer to that question is sort of known. It's something that people have thought about a lot and are working to understand, but there isn't a explanation that I'm super satisfied with. I think what I want to do is talk about, well, I could either talk about the tensor network point of view, or I could talk about scrambling. I don't think I'm going to have time for both. And I have a feeling that whenever I talk about tensor networks, that people are thinking like, what the hell is he talking about? So should we go to scrambling, or do you want to see the tensor network?
Scrambling.
As much as possible.
Of which? It's probably mutually
We
exclusive.
should aim to learn the most about the most things.
Well, the question is, I will show you the tensor network if people have followed the previous things I said about tensor networks, but I got the sense that maybe they didn't make any sense.
Does that have any quantitative prediction?
The tensor network?
Yeah.
It predicts the island. Is it quantitative though? No,
Yeah.
it's not.
Yeah.
But it does immediately predict the island, which I think is pretty cool. I have to draw the same picture for these two discussions. So maybe I'll try to do the tensor network one kind of quick, and then we can talk about scrambling for the rest of today. So, all right, so let me do this tensor network kind of quickly. I'm going to separate space into 4 regions. I, B, no, that one's called G, sorry. G, B, and R. Okay, it doesn't really matter what shape I drew them, but this is a spatial slice that I've separated into 4 regions. And R is the same as before. Okay, so R sits out here at 10 to the 6 Schwarzschild radii. This new separation here is, let's say, at like 10 Schwarzschild radii. That's the separation that I mentioned earlier. Gravity is important on this side, and gravity is not important on that side. Okay, so the way you should think about this is sort of we want to sort of have a holographic point of view where we live in a non-gravitational world, It's not quite true, of course. Gravity can reach out here, but gravity's not that important out here. And we're probing a black hole. Okay, so like we could throw stuff at it, see what comes back, that kind of thing. And you should think of the black hole as starting here. Of course, the black hole doesn't really start to the horizon, but it's really the black hole plus the stuff around it, which is gravitational, and therefore you should think of that as kind of the gravitational system that you're interacting with that you'd like to have a holographic description of. Okay, so we're thinking of gravity being important on these two regions and not important on these two regions. Okay, so the toy model for islands is the following tensor network. So, well, let me draw it. I'm going to draw, I'm not going to draw like a million tensors. I'll just draw one for each region. Okay, so there's, we'll say one big tensor for each of these regions, I, G, B, and R. Now, I'm taking a holographic point of view. Okay, so now what I need to do to turn this into a tensor network is I need to tell you the physical, I need to draw the physical legs and the internal auxiliary legs that encode the entanglement. So the first question is, where do we put what are the physical degrees of freedom of a quantum gravitational system? And for this, I'm just going to assume, we're doing toy model here, I'm just going to assume a holographic picture where the only degrees of freedom associated to I and G live at the boundary. Okay, so I'm not even going to draw any physical legs on I and G. I'm going to put all the physical legs out here. Okay, so region B, so region R, that's just quantum field theory. These physical legs are like the Hilbert space of some propagating fields in your quantum field theory. So these physical legs are just ordinary quantum fields. In region B, we have two types of physical degrees of freedom. There's the physical degrees of freedom associated to the quantum fields in region B, and then there's some holographic degrees of freedom that are associated to the fact that there's gravity.
It's pretty weird for G not to have physical degrees of freedom because it's outside of the black hole.
Yeah, but there's gravity there, so.
Yeah, but you could like go there and.
Yeah, but that's, yeah, I agree it's weird, but that's holography. The same is true like in anti-de Sitter, that all of the only physical legs of the tensor network are at the boundary, even though you can jump in and do stuff locally. Okay, so then there's entanglement between these, which is like dictated by the area. Okay, so remember that the amount of entanglement in the tensor network is like the geometry of the spatial slice. And so the amount of entanglement on this network is the physical area of these separation points. So these are area terms. That's like how many, that's the rank of those lines that I'm drawing, or how many lines we draw connecting the regions.
Why do we, well, is this the most efficient tensor network? I mean, or would it be more efficient to replace some of those lines with lines directly connecting, for example, I and R?
I don't know. It's just a toy model. It's just a toy model that's going to capture the physics of this. Okay, so we're not quite done though. If we just had a black hole, we would be done. The area, the physical geometry encodes some entanglement of some underlying unknown quantum gravity degrees of freedom, and we would be done. However, we're missing something here, which is the Hawking radiation. Okay, so the Hawking radiation is not included in the area term. The area term is the entanglement of the underlying quantum gravity hidden degrees of freedom. The Hawking radiation has extra entanglement on top of that. So we need to draw we need to put in extra tensors in this tensor network that entangle the Hawking bits in the black hole interior with the Hawking radiation that's escaped to infinity. Okay, that's it. That's the tensor network. So this is a toy model for the quantum state of an evaporating black hole. It's evolving in time. Okay, so how is it evolving? Well, it's growing more legs up here, and it's losing legs here. The black hole is shrinking, but the amount of entanglement in the matter fields is increasing. Then what are we interested in? Well, we want to calculate the von Neumann entropy of these physical degrees of freedom here. That's the Hawking radiation. That's region. We want to calculate S of rho sub r. And the von Neumann entropy in a tensor network like this has exactly the properties that I've described for the page curve. We could see that, for example, by cutting pieces off the tensor network. So when you have a sufficiently complicated tensor network, remember that you can calculate entanglement just by asking how many bonds do I have to cut to remove a region from the network. Okay, so at early times when there's not much of this Hawking radiation, you can cut region R like this. If there's very little Hawking radiation, then that's a good way to cut region R off of the tensor network. And that'll give Hawking's calculation of the entropy. Notice that the more Hawking radiation there is, this contribution to the entropy will be growing. But after a long time, now there's lots of Hawking radiation, more like I drew it here, with lots of those lines going there. And then a better way to cut region R from the network is to cut it like this. That's a more efficient way of removing R from the network that requires fewer cuts. And that's the appearance of the island. It's when you switch entanglement cuts, this region I is now linked to your region R. And it's a general property of quantum codes that in situations like this, you can take operators on this piece of the network and push them through the network using the circuit itself, using the tensor network. You can form operators in region R which act as operators on the stuff in region I. So that's how bulk reconstruction works. It works by pushing operators through the tensor network to all the pieces where it's connected. Okay, let's not get stuck on this too long, but if there's a quick question, I'll answer it.
So the fact that you were able to invoke holography in this kind of space-time, is that because there's like an ADS2 factor in your horizon region?
No, it was just me declaring this is the toy model I was going to look at, and then no, there's no reason I should be able to do that. I'm just saying that this tensor network has qualitatively the same properties as what we saw from doing the island calculation.
So it is assuming holography in this kind of a space.
Yeah, it's a toy model. I don't know. I wouldn't say it's. I don't know. It's showing that a holographic sort of picture seems to capture the physics that we found from the island rule. I would say that.
And we could also do the same thing in the ADS setup with a bath connected, right?
Yeah.
Yeah.
Then region B, you're in the. Okay. for the people who know what I'm talking about, if you don't know what I'm talking about, close your ears. For people who know what I'm talking about, if you have a ADS connected to a bath, region B, you should think of that as the point at the ADS boundary. It's the point that holographically encodes the gravity region, but does not include the bath. I said I was going to use that picture again. Yeah, let me use that picture again so we know what we're talking. Not yet. We'll come back to it. Don't let me erase that board. I'm going to try. Okay, so the last thing we're going to talk about today is scrambling. So the idea of, I'm going to start out very vague, and then we're going to come back to the black hole, and it'll be less vague. The idea of scrambling is that we have some quantum system with n degrees of freedom, and we drop a qubit into that quantum system. Could be up or down. And then that quantum system evolves according to a local Hamiltonian. What it means to be local is that if there are n degrees of freedom, the Hamiltonian acts only, say, only on 2 at a time, or only on 10 at a time. It doesn't matter how many at a time, but it's not like it's not some crazy random unitary. It's something that acts the way Hamiltonians do by coupling a few degrees of freedom at a time. Okay, so we take our qubit, we throw it into this big bath of n degrees of freedom, and then we evolve under a Hamiltonian that acts locally on those degrees of freedom. And then we ask, how long before the quantum information in this qubit thermalizes across the n degrees of freedom. Told you it would be vague. But roughly what we mean is we want it to spread out over all n of them. So like if I just gave you any subset of them, you would not be able to reconstruct the qubit. But if I gave you most of them, you would be able to reconstruct the qubit. If that's the situation, then we say that it's scrambled, or it's thermalized across the. Thermalized is not a great word for it. Scrambled is really a better word. It's that the quantum information has spread across all n degrees of freedom. Now there's a conjecture of Sakino and Susskind, which is called the fast scrambling conjecture, which has 2 parts. The first part is that the scrambling time in any quantum system is bounded below by log n. It's for any quantum system with say only pairwise or point clustered interactions. The second part of the conjecture is that black holes saturate the bound. I'm not really going to talk about the first part at all, but it's something you can motivate, for example, by looking at random quantum circuits that act pairwise. The fact that black holes saturate, we're going to talk about. And this fact that black holes saturate, so actually there was an earlier calculation or proposal in a paper called Black Holes as Mirrors, That was the name of the paper. It's usually just called Hayden-Preskel now, after the authors of that paper. And they considered the following, they asked the following question. Well, basically they did this but for a black hole. Okay, so they took a black hole. So they consider the following experiment. Collect the radiation until some time that's after the page time. Okay, so you make a black hole in a pure state. You let it evaporate until you've collected enough radiation to be after the page time. Then throw in one more qubit. And the question is, how long? Oh, and then you keep collecting radiation, and you ask, how long before I can read the qubit? And this, I think Hayden-Preskel's in one of the presentations next week too, but this will just be the 2-minute version, and its relation to islands. Okay, so is the experiment clear? The reason this paper is called black hole as mirrors, is because their argument was that the answer is basically right away. That when you've already collected lots of qubits, you could throw in one more qubit and then collect like just a few more Hawking quanta and get your qubit back. They argued this based on properties of quantum error correcting codes. They modeled the black hole plus qubit plus radiation as like a sufficiently random quantum channel. Now, it can't come back right away, okay? So it can't come back immediately, and this has to do with no cloning. Okay, so why is this a potential problem? Well, suppose I take my qubit. Well, the reason is the qubit still exists in the black hole interior. Okay, so we should be a little worried that you're able to get the qubit out in the radiation because it still exists in the interior, and we know that by linearity of quantum mechanics, you're not allowed to clone a quantum state. Okay, so when you do this experiment, you should be worried because here I am out here somewhere. Well, if I draw the picture this way, it looks silly. I can keep feeding the black hole to prevent it from ever evaporating away. So I don't really have to draw it that way. I can just keep feeding it matter so it doesn't evaporate. So the problem is I've collected the qubit out here in the radiation. The qubit still exists in the interior. So what if I collect it and then I jump in and now I have 2 copies of the qubit? I've violated the no cloning theorem. And I'm going to necessarily see problems with the quantum mechanics if I'm able to jump in and have 2 copies of that qubit. What saves you here is the black hole singularity. Okay? Now, if that qubit is headed to the singularity, so as long as it takes a little while, as long as you have to wait a while to reconstruct the qubit, it becomes impossible to jump in and have both and be able to put both qubits next to each other and violate no cloning. So you can use that thought experiment, the one where you collect the qubit, jump in, and try to put the qubits next to each other. You could turn that into a calculation and calculate a minimal time for the qubit to come out, and you get this log n, where log s, the log of the black hole entropy, by requiring no cloning. Is the question?
Yeah. You're saying you have the qubit on the outside, but do you really? You have the ability to do operations on your states in the Hawking radiation to reconstruct it.
Yeah.
Does that mean you actually have it? You haven't actually.
It does. Yeah. It means that you can follow an algorithm. Think of having a quantum computer that can act on the radiation. There's an algorithm you can use to distill that qubit into like some spin. So you have like this quantum computer and you have an auxiliary spin. And to be able to have the qubit means that you're able to distill that qubit. And then you can put it in your pocket, jump in the black hole, and try to violate no cloning.
So then, but if you perform those operations on the Hawking radiation with the quantum computer, then you've also applied those operations onto the island.
Well, we didn't get to the island yet. Yeah, let's see. Okay, that's going to confuse me, but let me get to the island. Let me come to the island in a minute.
Maybe you don't need to do any operations. You just like have your quantum radiation. You like put it in a box. And then jump in.
Well, it's going to weigh as much as a black hole, so that could be a problem. I don't think you can do that. But let me just say the punchline, and then we'll be done. But people can ask questions. Okay, so. So no cloning places this lower bound, and actually the coefficient is meaningful too. There's a beta over 2 pi, and they conjectured based on random complex quantum circuits that this scrambling bound is actually saturated by black holes. Okay, so they conjectured that the time it takes to scramble in a black hole is log s. Now I should emphasize this is a very short time, okay? so beta is like the light crossing time of the black hole. So beta for say a stellar mass black hole, beta is like a kilometer in seconds. Okay, so that's pretty small. Now S has m Plancks in it. Okay, so S is huge. S of a black hole, of a stellar mass black hole, is like 10 to the 70 or something. But there's a log. Okay, so this is a quantum gravity effect, but it's a log of that. So in fact, the scrambling time of a Schwarzschild black hole is only like 70 light crossing times. So the amount of time it takes to bounce a photon back and forth across your black hole 70 times, that black hole has now scrambled. So that's how long it takes. If you drop something into a black hole, that's how long it takes for that qubit to be mixed among all of the S degrees of freedom that make up the quantum black hole. It's very fast. It's very fast. And yet it's a quantum gravity effect with M Plancks and stuff in it. So the punchline of all this discussion is that if we go back to the island picture, the position of the island, the location of the island, boy, I got to draw a new one. This is, okay. Okay. Again, we have the 10 RS, and we have the 10 to the 6 RS. And we're collecting radiation out here on the second one. is our region R. And the question that I want to ask is, so we said there's an island in the black hole interior. The question is, where is the island? In other words, like at what time? It's somewhere along the QES is somewhere along the horizon here, but where? And the answer to that question is exactly where you'd expect from Hayden-Preskill. Okay, so it's a little complicated to say what you expect. So let me just do this in pictures, and hopefully this will make sense. Because you really have to kind of think about this. Like, so what do you expect? Well, the quantum system that we're interacting with is this gravity region that extends out to order 10 Schwarzschild radii. You should worry about that 10. That 10 is a subleading effect, so it could be 20 or 7 or whatever. Okay, that's our quantum system. So you should think that it takes a long time to throw a qubit 10 to the 6 kilometers, but that doesn't count. It's not until it hits the quantum system that it starts to scramble. Okay, so the idea is that you throw a qubit back here. So this is your qubit. You throw it into the black hole. It hits the singularity. That's the gravitational description. But we're arguing that a black hole is a fast scrambling quantum system. So I wish I had like use my bag. Okay, so you're supposed to hide everything behind this and just look at the outside and think of that as our quantum system that we're throwing something at. Okay, so we throw the qubit. It hits the quantum system here. It takes a time log s to scramble. And then it is emitted back to us in the Hawking radiation. Okay, so if black holes are fast scramblers, then this picture is showing when we should receive our qubit back, when we should get that information back. We should drop it in, wait a time log s, and then wait for it to come back to us. That's when we should get it back. And if you do the island calculation, the island will now be exactly here. Because see, the island is moving up as a function of time. And so if our region R, if we didn't wait long enough, like if we have a region R1 down here, we didn't wait long enough, we didn't get our qubit back, then that would have a region I1 here. And the qubit is not accessible in region I1. So this island agrees quantitatively. It gets everything. It gets the beta over 2 pi log s, just as Hayden and Preskill predicted, and was part of this whole fast scrambling story. All right, that's it.